Okay, so welcome to this WiP seminar. So first I will quickly introduce our group, the Women in Physics group here at Technical in Lisbon. And then I'll talk about the format of this event, and then we can start. So our Women in Physics group is a group of mainly students. And our goal is to work towards attracting and retaining more women in physics, in particular here at our university in Technical, but also in general. And this seminar series is one of our events. And the idea behind these seminars is first, of course, to hear about great research. And second, also to discuss the experience of working in physics when you're not a man, so when you're alone. So the format of this event is that we have the scientific seminar during the first 45 minutes. So there will be some time for questions at the end. Then we'll have a 10-minute break. And then for whoever is interested, they can stick around in this Zoom meeting. And we will have about 30 minutes of informal conversation with our invited speaker, who is Caterina Riconda. Okay, so if you have any doubts, just write in the chat and we will answer. Okay, so I'll introduce our speaker now. So Caterina Riconda, maybe many of you are familiar with her work. So she is the leader of the Plasma Theory and Simulations group at LULI in Paris. And she's a professor at the Sorbonne University. And she has studied different topics in plasma physics, such as plasma kinetic theory and laser plasma interactions. So Caterina, please go ahead whenever you're ready. Thank you.
Okay. So first of all, thank you for inviting me and having me here. And as I already mentioned to the organizer, I wasn't sure about how much in detail I should go. So I tried to be quite general, but you will forgive me if some parts are a bit too technical. So I'm going to talk about relativistic electron acceleration in laser plasma interaction and high intensity plasmonics. And my name was said is Caterina Riconda from Laboratoire pour l'utilisation des lasers intenses in Paris. And I also work in a framework of other plasma physicists, that is this Laboratoire logo that I'm putting here. Okay, so what I want to present you today is the idea that with laser interacting with a plasma, we can create a miniature particle accelerator. And when I say miniature, I really mean tiny, because the idea is that a laser that interacts with a plasma, if it has a high intensity, it can produce electric field that are of the order of teravolt per meter. That is, there are 10 to the 4 times larger than what you have in conventional accelerator. So that basically over some centimeters, you can really accelerate particle to very high energies. So it's small. And just for the notation, for the people that are not familiar, when the intensity of the laser is ordered 10 to the 18, we talk about relativistic intensity, because it means that the motion of the electron in such lasers if order of the velocity of light. So it's relativistic. And also, I'm not sure if everybody's familiar with plasma, so I rather introduce them and get rid of this question. So why do we talk about laser plasma interaction? Basically, because when you give energy to a solid, you create a liquid. Energy to a liquid becomes a gas. Energy to a gas becomes an ionized gas, where the particles are charged and are separated. And they're very sensitive to the electromagnetic field, is the main force that is important for them. And if you consider an intense laser on matter, you immediately create a plasma. So when you have interaction of laser with matter, intense laser with matter, in reality, you talk about laser plasma interaction most of the time. Okay. So what are the two possibilities of high intensity laser interacting with plasmas? There are basically two important schemes that are well known, and they depend on the kind of plasma that you consider. So one possibility is that the laser propagates inside a so-called underdense plasma. So what does this mean? If you consider a laser with a given frequency, that is typically the frequency for visible light, order of 100 of terahertz, if this frequency is larger of a reference frequency of the plasma, that is called the plasma frequency, and the formula is given here, you have that the laser can propagate inside. That means that the plasma is transparent to the laser, so it can go through. And in practice, if you consider plasmas that are made from gas and they have typical electron density 10 to the 18, 10 to the 20 particle per centimeter cube, you are in this situation where the laser can propagate inside this plasma because the frequency is higher than the plasma frequency. This kind of interaction is a volume interaction. Second possibility is that you consider plasma that are very dense. If a plasma is very dense, then we talk about overdense plasmas, and the typical frequency, the frequency of the laser that is still visible typically, in this case will be less than the plasma frequency. And if the frequency of the laser is less than the plasma frequency, and this happens, for example, if you have density of plasmas that are created starting from solid density, that is 10 to the 21, 10 to the 22, 3 particle per centimeter square, the plasma behaves as a reflecting medium. So the laser cannot go through and it will be reflected. However, it's not complete reflection, but it's only partial, especially if you consider high intensity. Indeed, if the intensity is large enough, you will have some surface interaction. Can you see my mouse? Yeah, okay. So yes, you will see some surface interaction from the laser and the plasma that, as I said, is not completely reflected, but at the surface will still be able to interact with the plasma. This interaction will be mainly with the electron and can create currents inside the plasma, very important currents that can be of order of 10 to the 6 ampere. And these heated electrons, they can then propagate behind the target and accelerate ions because they left behind charged particles, positive charged particles that are then accelerated, or they can also emit gamma ray or X-rays. And so this surface interaction through the electrons becomes also an interaction that allows acceleration of particles and production of gamma. So I'm going to talk about these two schemes. The first one, acceleration of electrons in underdense and overdense plasma. So going back to the underdense case, there is a very successful way of accelerating particles, that is the wake field acceleration that happens, as I said, in very low density plasma. So basically, the laser beam, as I said, can propagate through the plasma. And while it propagates in this interaction, it can excite electron plasma waves that are typical waves, normal modes of the plasma. These electron plasma waves, they are longitudinal waves, that is, they propagate in the same direction of the electric field, and they are able to accelerate electron beams to very high energies. These electron beams, they are either coming directly from the plasma or they can come from outside. So you can excite the wave and inject electrons inside the wave and accelerate them. And these are some typical results that have been obtained already some time ago, where you can see that you can obtain electrons at the energy of 180 MeV with very, this is what I'm showing here, the energy of the electron in this part. And here I show a typical example of the size of the beam of electron that is accelerated. So it's a very collimated and nice beam. And all this happen over like 1 millimeter. So it's really a miniature system to accelerate particles. If you consider very high intensity, this technique of accelerating electron through plasma waves enters in a regime that is particularly interesting, that is called the bubble regime. This is what I'm showing here. So basically, again, so this figure here shows a plasma, that is the blue. A laser pulse has been going through the plasma, and by going to the plasma, it excites this wave that becomes, in fact, they are not standard waves, but non-linear waves, where basically you evacuate all the electrons in a certain area, in a bubble, that's why it's called bubble. And since all the electrons are gone, inside this bubble, you create a constant electric field that is very strong and positive, and that will be able to accelerate, test other electrons that by chance get injected in the right position. So this is basically the idea behind this wake field acceleration. Either you excite a regular wave or the laser creates a hole that is a variation of a regular wave. And this a hole of electrons where only the ions stay, and this field can accelerate particles. So this was predicted numerically, and then it was also observed experimentally. And again, I'm showing here some nice results where you can obtain almost more energetic electron beams at JeV by this wake field acceleration at very high intensity. So this is very nice. It's very powerful, and instead of having big synchrotron machine, you can have very small and compact acceleration. However, the only let's say problem related to that is that you start from very low plasma density, and then you have few electrons that are acceleration. So the current that you create with this technique of the wake field, the laser inside the underdense plasma, is few electrons. And however, you can think about schemes. I mean, since it works very well, you can also think about schemes where you can obtain even higher energy of electrons by combining multi-step. So every one of the steps that I'm showing here can be an individual acceleration by laser wake field, or you can also combine different system of acceleration like standard with wake field. So, but as I said, one of the drawbacks of this model is that the density is not that high, so you have small currents. So you have the other acceleration mechanism, that is the one that happens at the surface, that is also interesting. And this happens when you consider very high intensity, because otherwise the pulse is reflected, the laser pulse is reflected. And also when these very high intensity pulses arrive at the surface, and they are very short, the surface stays steep. Because basically, as I said, when an intense laser interacts with a solid, it will be absorbed, it will create a plasma. And if the plasma is very hot, the plasma will expand. But if the laser is short, it does not have time to expand, and you can consider a steep density plasma. So this is the scheme I'm talking about here. So you could, I mean, how does this work? Well, basically, is the force of the laser, the electric field of the laser, that can penetrate a bit inside the solid. Basically, it will penetrate inside a skin depth. And for strong laser, is strong enough to push the electrons out of the plasma back in vacuum and send them back in. But since the plasma is a perfect conductor, inside the plasma, there is no more electric field, is screened by the plasma. So the energy that the electrons have gained because of the laser field, they will keep. So this is basically, it's called vacuum heating acceleration. And it can also work if the electric field is parallel to the surface, because then you have the Lorentz force, the V cross B force, that is able to bring back and forth the electrons and heat them. So as I said, this is another technique of transferring energy to the plasma. I have not talked yet about acceleration that you get from this. It's called vacuum heating. And here what I'm showing to you is some example of simulations that show this phenomena. So basically the laser arrives inside the skin depth. And as you can see here, you have particles, if it's a function of time. The particles, they don't move in time, but then when they see the laser, they start being pulled out of the plasma and then back in. And when they are back in, they keep their energy and they hit the plasma. So this is the surface acceleration. And we have a scaling law to calculate how much of the energy of the laser is transferred to the particle. And the important thing is that then, since the plasma is partially reflecting, only 10–30% of the energy of the laser is absorbed. And of course, when the laser stops, the heating stops. And this is a difference between these mechanisms of transfer of energy from the laser to the particle and the one that I mentioned previously, because in wake field acceleration, you excite plasma wave, and plasma wave, they can also survive without the laser. Okay, so how do we use this acceleration at the surface, this transfer of energy at the surface? Well, as I mentioned already, this can be used in order to accelerate ions. So basically, the laser accelerates the electrons, hits them, they get injected into the target, they go to the back of the target. Since they go to the back of the target, they are hot, they move with their energy, they go away, they leave behind the positive charge, and the positive charge, they feel the electric field due to the difference of the space charge is called, and they are heated, and they are accelerated. And so this is also what I'm showing here. Behind is some measurements of ion acceleration by this mechanism that is called target normal sheet ion acceleration. So wave field, you accelerate directly electrons through volume interaction, and instead surface interaction, you heat electrons that accelerate ions. These are the two mechanisms. So I didn't do, I'm going to talk about my work now. So the previous mechanisms are well-known mechanisms. And one thing on whom I've been working a very long time, and that I'm going to present starting from now, is a scheme that combines both ideas that I introduced. So basically, the idea is to consider interaction of the laser at the surface, so with a very dense plasma. But instead of using vacuum heating, the idea is to excite a wave at the surface of the plasma. Like in wave field, where you excite wave inside the plasma, now you excite a wave at the surface. So this is what I'm presenting here. So it's the idea to combine the two previous schemes to have interaction of a laser with a dense target, but an interaction that is able to excite a surface wave. So some of you might be working in solid state physics or plasmonics. And so if you do that, you are already familiar with this mechanism, because you probably know that you can excite plasmons that are surface modes, that was I'm showing here, at the surface of a metal with a laser. And normally these plasmons, they live between the metal and the dielectric. So here the idea is exactly the same, except that, as I said before, when the intensity of the laser is high enough, the solid becomes a plasma. And instead of exciting plasmons, you excite what is called surface plasma waves that have very similar characteristics to plasmons. The important thing about these surface waves is that they're both orthogonal, transverse, and longitudinal. They propagate along the surface, but they have both a component perpendicular to propagation and one parallel. Okay, so how do we use these plasmons? So first of all, how do we excite them? This is one of the problems. How we make sure that the laser creates the plasmons. So one thing that you have to know is that it's not possible to excite a plasmon on a flat surface of a homogeneous target. This is because the dispersion relation of the laser and the dispersion relation of the plasmon, they cannot match if the surface is flat. So in order to excite surface plasma waves, you need gratings. And the grating that have a periodicity here given by this A that I have, will allow you to have the matching condition for resonance excitation. So long story short, in order to excite surface plasma wave, if you have a given laser frequency or wavelength, a given density, and a given grating periodicity, you have an optimal angle that is needed, a resonant angle that will allow you to satisfy the dispersion relation and excite surface plasma waves. So you have particular condition to excite this wave. It's not just a laser impinging on any surface. And as I already mentioned, these surface waves are interesting because they have both longitudinal and perpendicular field. So we looked at this very long time ago. So it was like more than 15 years ago, theoretically. And we found that if you excite surface plasma wave via grating by a laser, you can increase the laser absorption up to 70–80%. So you remember before, when I considered the laser impinging on a flat surface, I said the absorption was order 20%, 30%, and now you increase a lot the absorption. And if you increase a lot the absorption, also the ions that are accelerated at the back, they can be more energetic. So it's a very efficient way of improving ion acceleration. So how did we demonstrate this? We did this with peak simulation. So I don't know if you're familiar with peak simulation, but basically these are simulations where you consider the interaction of the electromagnetic field by the Maxwell equation with the particles that create the plasma, where particles, not every single particles, but macro particles that are representative of the plasma. So these simulations, they allow you to study the interaction of the plasma with the laser. So this is what we did. We did some simulations, and as you can see here, I'm showing. So this part here is the plasma. The laser is coming from one side, is impinging along a flat surface. And as I already said many times, most of the laser is reflected and part is absorbed at the surface. And you see that this pattern creates, that is the sum of the laser coming and the laser reflected. That's why you have an interference pattern. So you know that in this simulation, most of the laser has been reflected. Below, instead, I'm showing the same thing, but instead of having a flat surface, I have a modulated surface that you don't see super clearly here, but there is a modulation. And I consider the resonant angle. So you can see that the field here is completely different because you have these are lines at constant field of the incoming laser. And you don't have the interference pattern because the laser is not going back, but instead is exciting waves that are this bunch here along the surface that they propagate along the surface. So with the good conditions, the laser can indeed excite surface plasma waves. These surface plasma waves are localized at the surface, so they're evanescent in one direction and also in the other, inside the plasma. They propagate along the surface. And their field is large because you can imagine all the energy of the laser is compressed in a small zone, and so they can have very high field. Why do we need particle simulations to study this wave? Well, because on top of exciting this surface plasma wave that you could describe even with fluid models, you have that these waves, they then interact with the electrons and hit the electrons. And in order to describe the interaction with the electrons, you need kinetic simulation, you need particle simulation. So this is still a result from the same work that I just presented. So we measured how much of the energy of the laser is absorbed in a flat surface. So this is the incoming pulse. So the laser pulse has a shape, and when it's reflected back by it's a bit reduced, 24% is absorbed. But when you excite the plasma wave, you see that the same laser, the part that comes back is much less, 72% is absorbed. In the code, we can also measure the distribution function of the electrons, so we can check how much they are heated. So again, this is what I'm showing here. This is the case of the flat surface. This is the case of the surface wave, and you can immediately see that the maximum energy at which the electrons are accelerated is much larger with the surface plasma wave. And also the temperature, the slope here, as opposed to the slope here, is much larger. And actually it's 10 times larger than the scaling that you would expect normally from the interaction at the surface without surface plasma wave. So as a result, these hot electrons will go through the target. They will accelerate proton at the back. So this is the proton that go out here. And again, in the simulation, we can check that if there is a flat surface, you can accelerate ion up to 7 MeV. And instead, if there is the surface plasma wave, you can double the energy of the accelerated ion. So this was a theoretical work that we did some time ago. And it motivated the experimentalists to do some experiments. And it did confirm, so this is what I'm showing now is experimental results. And you can see here that when you are at the angle of resonance, the energy of the proton that has accelerated from the back is twice in the case of excitation of surface wave. So this theoretical work was confirmed by the experiments. Okay, so I'm already almost done, but okay, I'll speed up a bit. There is another interesting phenomena that happens with surface plasma wave, and is in which direction you accelerate the electrons. So when we start, I went chronologically in the presentation. When we started studying surface plasma wave, we just wanted to increase the absorption of the laser and the general absorption of the electrons. But when we look at the distribution function of the electrons, and this is what I'm plotting here, even if it might be not transparent for you, there is a very interesting feature that is this line here. This line here tells you that most of the most energetic electrons, they are not accelerated inside the target, but along the surface. And this was also confirmed when we look at the density of electron, that is what I'm showing here, along the surface. You see these bunches of electrons that are very fast and they are along the surface. So this was a bit of a mystery when we realized that, because it's true that you expect acceleration along the surface because you have a field that is both along the surface and perpendicular. But if you look at the surface plasma wave, the parallel field is much less than the perpendicular one. So you would expect that these one are not the fastest electron, but the slowest, and that the fast one are the one inside. As a matter of fact, is not the case, and there's a good reason why. I mean, we understood why they have to be accelerated parallel to the surface. And this is related to the fact that this wave has a very high phase velocity. So this wave, they propagate along the surface at relativistic velocity. And so Vphi is order of c. And instead of talking about velocity, we can talk about the Lorentz factor related to this propagation velocity. And it has these waves, not only they have very high phase velocity, but also they are such that if you put yourself in the reference frame of this wave, they become electrostatic. So it means that you can calculate a potential, that is what I'm showing here. And the particle that, so the particle that start from the top of the potential and arrive at the bottom in the parallel direction, oops, sorry, they can gain a lot of energy. So you trust me on this because it will take too long to explain this in detail. But if you study the bottom line, if you study the characteristic of these waves, you discover that indeed, because they are electrostatic and because they're very fast, you can accelerate electrons parallel to the surface at very high velocity. And you can calculate how much you accelerate that. And this is what I'm showing here. So basically, you can calculate the energy of the electron in the parallel direction. And you can see that it's true that they are proportional to the parallel field that is small. But this is multiplied by the gamma factor of the phase velocity to the square that is very large. So they can get really high velocity. Only problem is how you make sure that one particle arrives at the top of the potential, how you make sure that you have particles that can actually feel this acceleration. So again, I will go quickly on the next step because it's a bit technical and it's already a bit late, but we studied that as well. And we figured out that effect is the perpendicular field that helps the particle to go to the top of the potential. So basically, why? Because of the Lorentz force. So as I said before, the perpendicular field, the transverse one, is larger than the parallel one. So you would expect larger acceleration in this direction. But instead, is not what we find. However, the fact that this field is large, it gives an initial kick to the particle in this direction, that then is deviated by the Lorentz force in this direction. And when it's deviated along the surface, it can go to the top of the potential and be accelerated. So it's what we call the self-injection, two-dimensional because it's done by the transverse field of the surface wave field. And so here is an example. I don't have the energies, but you trust me, this particle is much more energetic than this one. This one gets a kick by the field. So it goes inside from the plasma, inside the potential at the top, and then it stays and is accelerated parallel to the surface, not completely parallel, of course, but basically parallel. And this one instead doesn't see the good field. So it just kick in one direction, then back in another, and then eventually it gets ejected out. So it really depends on the dynamics of all this complex field altogether. So this acceleration along the surface was also observed experimentally. So there were other experiments that were done later. And one point that I didn't mention before is that when you want to do this kind of experiment, you really need a very good contrast. That is, the laser has to be very clean, because if the laser has a pre-pulse that is intense, it can hit too much the plasma and destroy the grating. And the experiments, they did show, this is what I'm showing here, this acceleration along the surface. So is this spot here is the spectrum of the electron, and the angle 0 correspond to the surface. And you can see the difference here. You don't have a grating and you don't have surface wave excitation, and here you have it. And indeed, when you have it, you have this very strong acceleration along the surface. And again, these are self-consistent simulation of the interaction in conditions that are the same as in the experiment. You can see again that the particle goes out, then is injected in, moves a bit, but stay basically parallel to the surface and gets a lot of energy. And these are the different kind of resonant gratings. So you can see again, for different resonant conditions, we obtain these electrons that are accelerated, and the grating is not there. You don't have the electrons. Okay, so this was kind of recent, and we've been still working on this and finding about other schemes. So I'm not going to go too much in detail, but just give you a quick taste of other ideas. So basically, one idea, now there are lasers that they have that is called rotating wavefront. So the angle of the laser tilts as the laser propagates. And because of this tilting, you can actually make the laser follow the wave as you excite it. So basically the laser would come at a given angle and excite the wave, and the wave propagates, and then it separates from the laser. But if you have this tilt of the front, the laser can follow the way and keep transferring energy. So it can be a way of controlling the amplitude of the wave, but also of making narrower, because you are only exciting one bit of the laser, of the wave. And this is what I'm showing here. So basically, if you excite, this is a surface wave, is the magnetic field of a surface wave. If you excite a regular surface wave, it will propagate along the surface. This is along the surface with a certain width. And if you excite the surface wave with wavefront rotation, as it propagates, it's compressed, because you always propagate the same bit. It's like you follow this bit and you keep propagating and amplifying this bit. And so you can get higher intensity and shorter waves. And as I already said, since this wave, while they propagate, they also accelerate electrons, you can also have the same effect on the electrons. So what I'm showing here is the wave they propagate, and this is the electrons that are accelerated parallel to the surface. And you can see the wave is damped as it gives energy to the electron. So this is without wavefront rotation, is the large. So it's this one. And this one is wavefront rotation, is much narrower. And since it's more narrow and intense, also the electron, they have highest energy. So this is the momentum that is higher than in this case, and they're narrower. So there are ideas on how to control this acceleration with the laser. So what's next? Well, the idea is to go to higher intensity on this technique. Higher intensity because maybe you know that now there are multi-petawatt lasers that are in construction or existing already, and multi-petawatt laser means lasers that can get much higher intensities. So they could excite surface wave at higher intensity that can accelerate better electrons. And we know that even with very high intensity from multi-petawatt laser, we can excite with a grating the surface wave. But there are certain conditions because, as I mentioned already, you don't want to destroy the grating. So if the intensity is very high, you have to be careful. So this would be nice to have experimental verification at very high intensity. There are other mechanisms that I did not talk about of surface plasma wave excitation in laser created in channels. So at the surface of a channel inside a plasma, you can also excite surface waves. And if you go up to high intensity, there are other phenomena that, again, maybe you heard about, that is radiation friction due to the emission of photons or creation of positron electron pairs in a hot dense plasma. So to conclude, very intense laser plasma interaction has proven extremely successful in producing relativistic electrons and secondary sources, ions or radiation. So it's really miniature accelerator, either on volume interaction or surface interaction, but the scales are really tiny. So this is very nice. It's a big success of plasma physics. I talked about an alternative scheme on which I personally worked quite a lot. That is the idea to use gratings and the resonance excitation of surface plasma waves. This technique has advantages that it increases the coupling with the plasma at the surface. It can hit electron inside the target and then increase the proton acceleration, but also along the target. And there are other secondary sources that I didn't mention that we can also study with that. And I would like to acknowledge my group. So not all these people worked on this topic, but many they did. And some of these, they're gone. Some are still in my group because some were PhD students and or postdocs that now are doing other things. But all of them, they contributed either directly. So this is the list of people who contributed directly to the work, or indirectly, because we always discuss in the group what we are doing. So even if we do different topics, everybody is pretty much aware of what the others are doing. And also other colleagues at Laboratoire des Surfaces Irradiées. So it's another laboratory next to mine, and in the University of Pisa. Okay.
Okay, thank you very much. That was very exciting work on the acceleration of electrons. So we can start with the questions. So does anyone want to go first? You can raise your hands here on Zoom, or also write in the chat if you can't use the microphone. Okay, if there isn't a question for now, I have a couple of questions. I have a lot of questions, but I'll let you. Okay, I'll let Pablo go first, and I'll save mine for the end.
First of all, thank you very much for the presentation. My question comes from one of the last plots you showed. So if you can go back a couple of slides. So here, yeah. So maybe I'm getting confused, but I can see that at the bottom of the plots, there's this. That's supposed to be the grating, no? I guess.
Yeah.
So, but then I see that the wave propagates into a region where the grating is. So you don't need to have the grating all along the surface.
Actually, this is a point that we exploited in this paper that is quite important, is that not only the laser couples to the grating to excite the wave, but also the wave couples to the grating to emit radiation. Okay. So the idea is that if you make the grating only on half of the plasma in the place where the laser arrives, then you have the laser coupling to the plasma wave, but then the plasma wave, when it propagates, since the grating is not there anymore, it will not emit less radiation, and it will keep more energy. I mean, you have less losses. So you absolutely understood correctly. So it was done on purpose. The idea is just to separate the part of interaction with the laser and the part of propagation.
And I have a second part to this question, which is more of a curiosity. So how long can these waves propagate through the plasma surface?
They depends on the intensity, because basically they can propagate very long. What stops them is the damping or the losses by radiation. So if they are low intensity, they can really propagate very long because they will not dump too much. If they're high intensity, as you can see here, they are dumped very quickly. Yeah. Because this is the blue, the brown is the electrons and the blue is the wave. And this is 10 periods later, and you see in 10 periods how the wave was already dumped. Mm-hmm. So, but it can propagate, I mean, even when it's very small, they can propagate for a very long time. It's just, I mean.
Thank you very much.
Okay, there's another question from José Luis Figueiredo.
Hi, can you hear me?
Yeah.
Okay, so first of all, thank you for the presentation. It was really nice. I have a question regarding the function of the grating in exciting the surface plasmon. So you told us that you need the grating to match probably the frequency and the energy of between the photons and the plasmons, I think. But yeah. Can you detail a little bit on how that works and why is that really important?
Yeah, of course. So first of all, in general, to have resonant excitation that is efficient, you need both the frequency and the K vector of the way of the resonator and the way to match. So this, okay.
And now, we are talking about the wave vector and the energy between a photon of the laser and the plasmon, right?
And the plasmon, exactly. So you know the dispersion relation of light, of course, so that basically omega is K over C. And the dispersion relation of the plasma wave is this one.
Okay.
So it cannot work. I mean, I don't have the drawing, but you can plot both of them, and you see that they never cross.
So if you want to match the energy, you don't match the K vector and vice versa.
You need this extra. If I don't have this thing, and I use both this dispersion relation and the one of light, it will not work. You don't find any place where you can intersect.
Okay, so now let me ask you why. No, please continue.
No, just the grating is one solution. There are other solutions that is not to use a homogeneous. You can use like two different materials. I mean, in plasmonics, there are many different ways of exciting surface wave apart from gratings. But anyway, you have to change the dispersion relation to have the matching. It doesn't work just with a simple plasma or solid and laser.
Okay, and for the typical parameters you use, do you know what is the value of that A there, more or less?
Oh, yeah, it's micron, fraction of micron. It's not that constraining. It's order of it's close to the wavelength of the laser. The wavelength of the laser is about a micron. And I think.
And how do you produce the grating, by the way?
We bought it.
Okay.
It exists in.
Because you told that the laser could destroy the grating.
You can also produce it with the laser. I was going to say that.
Okay.
You can also produce with two laser impinging. So there was also an idea of having a scheme where you don't buy the grating, you start from flat. You use the laser to produce the grating and to excite the waves.
Yeah. Okay. Thank you.
Okay. Thank you. Is there any other question? Maybe, so Paulo asked some of the questions I was wondering. I was also wondering something else. So, so this is related to what Pablo asked. So he was asking about how long this wave can propagate, and you were saying the limitation is basically how fast the wave dampens. So the limitation for the acceleration of the electrons is this, right? It's how fast the wave dampens. Is there anything else that limits, or to which energies do you hope that you could accelerate these electrons?
Yeah, there is another limitation that is that you stay in phase. So basically, it's the same limitation actually that is in wake field acceleration for the people who are familiar. But basically, you get energy. Okay, let's say you start at the top of the potential and you get energy if you go up to the bottom. But if instead of going to the bottom, you go sideways, then you lose, you don't see the field anymore, you are ejected. So this is another limitation, is that you don't, we say you don't stay in phase with the field up till the end. And another limitation is, let's say that you go to the bottom and then you go up, then you lose energy again. So you phase in the parallel direction. So these are, but in practice, in all the experimental simulation, we never, I mean, we are before this dephasing condition.
Okay.
It's more the fact that the wave is damped that matters.
Most important fact. Okay. So we're almost finishing, but maybe there's time for one more question. And in the meantime, I'll already post some links here in the chat, just for information. Go ahead, Victor.
Thank you for the nice presentation. My question is regarding the divergence of this accelerated electrons. I mean, do you have like a comparison with the traditional method? Are they more divergent because of the grating, or there's no problem with that?
Okay, they're a bit more divergent, but I think it's, yeah, this is the size. So basically, yeah, this tells you about, they're a bit more divergent, but I think this is exactly why we were thinking about other schemes where you can control better the particles inside the excitation inside the wave. But yeah, they're a bit more divergent, but much less than what you have with NSA, if you're familiar with that. That's a huge divergence. Or also with direct laser acceleration is a large divergence. This is not a very large divergence. It's a bit more, but controllable.
Okay, thank you.
Okay, thank you very much again for the seminar, Caterina. So we will have a break now, a 10-minute break. We will leave the Zoom room open, but you're welcome to disconnect and reconnect if you want. And whoever is interested, stick around for our conversation with Caterina, where we can ask her questions about her career and anything you want, really. So yeah. And please, I would ask you, if you have a few minutes, please fill out our feedback form so we can make these events better in the future. And thank you very much for attending.
Okay, so see you in a short while.
See you in 10 minutes. Hello, welcome back.
Hello again.
Hello. So again, thank you so much for the seminar. That was great. I think it was very understandable.
Thank you.
Okay, so for this second part, so what I suggest for the format is that, so first maybe I can start interrogating you unashamedly and see if you, and we can wait a bit for people to ask their own questions and maybe lose the shyness a little bit. And of course, feel free to write in the chat. And Caterina, if at any point you're not comfortable answering a particular question, of course, you can just say that, and we'll move on. Okay, so I guess I have a couple of questions. So for me, the most basic question, the most basic questions start around this choice of career. So, so do you like doing research?
I love doing research, so it's an easy one.
Okay.
I really love doing research, and I didn't know that when I started. I didn't know at all. I didn't know what research was exactly, but I like to be independent. I don't like to be told what to do, and the research is good for that. And I like things that are difficult. And again, research is very nice. Sometimes it's frustrating. Well, okay.
Well, yeah, that's the price you pay, I guess, for that.
So you have to have a strong stomach or mind or whatever, because sometimes you don't go. You think you go somewhere, you don't go anywhere. But I like it. I like that you change subject regularly. You're not always doing the same thing. So no, for me, it was really nice. And I didn't know at all what it was. I just started, okay, I study physics, why not? And then I got more and more interested.
Okay, so so do you think that your let's say your taste for research came with time a little bit? That's
yeah,
what you're
because
saying?
I think at the beginning I didn't know enough about the topic, or in general. I mean,
how it works.
Yeah, but also just physics, there is a lot of technicality behind. It's like you have to learn a language, and when you learn the language, you can use it, and it takes a long time to learn the language. Yes. So that was a bit what it was for me, that really learning that, okay, I can use this language was not obvious.
Yeah, okay. And do you think that, so do you consider that it was a difficult path to get to where you are now in terms of your career?
It's demanding, yeah. It's demanding. It's not something simple for anybody. I mean, independent of gender. It's very competitive. Many times you do things and people don't pay attention to what you do. They don't read your papers, or so, and you don't know why. So it's demanding. So no, it's difficult. It's not easy. But on the other hand, it's up to you if you wanted to try to do things that are more appealing, or just do your day-to-day job, and you will still find results and do something nice. I mean, you can more or less decide your level of ambition. Yeah, but it's competitive. It's definitely competitive, and this is already when you do PhD.
Yes,
it starts. It doesn't become all of a sudden competitive. It starts immediately. It's
already a good sample. Okay, yeah. That's depressing. Well, not depressing. It's the way it is.
You have other things that are great.
Okay, we already have here a question from Maria. Go ahead.
So first of all, thank you for accepting to open our seminar series. We're very happy to have you here. And well, Sarah has a question actually for you.
Wow.
What are the if you would think back from the beginning of your career, what do you think are the most important turning points where you could have maybe said, okay, maybe I'm done with this and I would leave, but there is something that brought you back to research? So
It's funny because I never did that. I never said I'm done, I'm going to leave. So, okay, I have to say that getting the PhD in the United States, arriving to the end of the PhD was very important. So I never really thought I'm going to stop, but I was like, is this really what I want to do? And when I got to the end, so obtaining a degree, it sounds stupid, but obtaining a degree was a recognition. And it was the moment where I decided, okay, I got this recognition, so I can go for it. So that's probably was the only moment where I was really, you know, like hesitating. But otherwise, I don't have that often this, I mean, I don't think much, okay, I'm going to stop, I have enough. It's kind of, okay, it's not as great, but it will become great again. Or, you know, I know it's like that, it will pass. It helps also to have people around that work with you. I'm a social person, so I try not to isolate myself, and that helps a lot. That's very, very important. Because when you're a bit, someone else will be up, and when the other person is down, you will say, no, come on, let's go. So.
Okay, may I do another one?
Of course, yes, go ahead.
Yeah, so if you had now in front of you someone starting a career, what would be your piece of advice to give, something that you didn't know when you were starting yours?
That, okay, it's I would say trust yourself. That is kind of obvious. But when you're young, you expect your advisor to tell you that you're good, or that you have to do this well, and instead it doesn't work like that. Is not, you will not have people around you telling what you done is good. You have to believe it by yourself. So that would be my advice. Trust yourself. Don't expect the motivation or the validation to come from outside. It will not come from outside. It has to be your motivation. And this was not, I didn't know at the beginning. I was still expecting people to tell me, oh yeah, it's very good what you did, etc., etc. I mean, you always expect that, of course, all your life, but you know, not as much.
That's a really important message, I think. Did you want to ask anything else, Maria or Sarah?
Thank you. I'll be silent for now. Maybe I come back.
So Sarah, you have high expectations.
Okay, we have here a question from Beth, I think.
Hi, yeah, can you hear me?
Yes.
Great. I wanted to ask, so you were presumably, did your school in Italy, is that correct? In Italy?
Yeah, I did my undergraduate in Torino.
Okay, and then you moved to the US and now you're in France, if I understand correctly.
Yeah.
So I wanted to ask you, what are your reflections on moving abroad, living abroad? What's the good, what's the bad, what's your advice?
Okay, so I think it's very good. That is the proof, because I never went back. I left and never went back. I think education in Italy is excellent. I cannot complain. I mean, frankly, when I left, I had a strong background, a strong education, and it was important. But it's true that if you see different countries, each country has its own specificity, its own way also of doing science. Just very simple. In Italy, we do a lot of theory. In the States or in England, UK, it's more oriented toward experiments. There is more, I mean, not only there, but there are more experimentalists. We have theorists and experimentalists. In France, it's a bit a mix. It's a bit theoretical as well. So I think that's very nice to go in different countries and see how you look at different things. You ask different questions. It's also when you are in your own country, people know you from your background, your family. And there are some assumptions on what they expect from you. When you go abroad, you are like this new person that doesn't have a background. And this is both an advantage and a disadvantage. The advantage is that you have no constraints. And the disadvantage is that, of course, you have to prove that what you do is good. But you don't have the constraints. And that's something useful, because they take you seriously immediately. While instead, if you stay in your university, you used to be a student, you are the permanent student. I mean, this can work or cannot work sometimes. So this is an advantage, but if you are more protected, of course, if you stay in the same place. So that's.
Thank you very much.
Okay, so I have a follow-up to a little bit what you were saying about the validation and the confidence. So you were talking about the internal part, right? That you have to be confident in yourself. So, but so now I want to ask about the external part, because I think very often we think about to be successful in research, you have to project yourself as a very confident person. You have to be very assertive. So what's your opinion about this? Do you think this is true? Do you think in general, you have to be confident when showing your work to be successful? Or do you think this is not necessarily true?
No, I think it's true. Actually, there is one thing that I would have said to myself now, that is the importance of communication. That is that you don't only have to do a good work, but you also have to present your work in a good way. That is not easy. And you have to be not shy. So no, I think it's important actually to be also, I mean, science is a social thing. The study that you do keeps going because other people are interested. They give you feedback, you give them feedback. It's not something, I mean, some people, they work in their corner, but it's very rare. So I think that is also important, but it's not the only thing. I mean, you have to say, okay, sometimes some things will not attract the attention of my colleagues, but I still do it. But of course, if they attract the attention of your colleagues, then you have a dialogue, and then you learn more from what they tell you, you advance more, you're more efficient, it's more interesting, you get more motivated. So no, I think it's true that it's important. Communicating is important. And it's not always easy. And it's definitely something that when I was a PhD student, I did very badly. And I keep telling my PhD students that it's super important, and they are here, some of them, so they know. I keep telling them, you have to be a good communicator. It's important.
Yeah. Yeah, I think, yeah, there's definitely a social aspect to, to all kinds of work, but I think in science, sometimes people like to think it's a very objective effort, but no, you have to work with people, there's a social part of it, definitely. Okay, so I also have another question. So related to the moving around places, moving countries and so on. So did you ever feel like because of your career, because of this type of career, you had to make any difficult choices for your personal life?
Actually, that's why I'm in France, because when I was in the States, they proposed me to stay there for postdoc and maybe have a career there. And that was tempting because it's very nice environment, and job-wise, you really have lots and lots of support. But I decided that I couldn't live there. It was too far from my family, and it was too difficult. Frankly, I didn't like the idea. And I ended up coming back in France. That was great as well. But it was definitely dictated by personal choice. It was not, the work environment was great, money was great, everything was nice, but
just not the geography.
Yeah, for me. And so that's personal choices that enter. Also, I had a baby as soon as I became permanent professor. So that's was not really a choice. I mean, it's not that I said, okay, I wait until I'm permanent professor to have a kid. I mean, didn't work like that. But it's true that once I was permanent professor, I was more relaxed and it was easier.
Yeah.
And actually combining work and baby for me was nice. France is very good for that. It's a very good environment to help working moms.
Okay. Yeah.
So it was great. But again, it was not exactly a choice, but yeah, it happened like that. And I think I'm the only one. Although I have friends that did their babies when they were doing PhD, when I was in the States, but I thought it was very difficult.
Yeah, well, especially in the United States, you probably have a lot less support.
Yeah, you need to have more money for daycare and stuff. So
yeah, this is something that will depend a lot on the place where you are, I guess, the kind of support you get. I don't know if there's any questions in the meantime. There's one by Joanna.
Hello, thank you for your presentation. Also, I really enjoyed it. It was really clear. Thank you. Talking about communication, I guess for me it's a big problem. I would like to know if you have some suggestions on getting it a little bit better or some advices. And also because, well, you had to move already 3 times, so you have to face the barrier language too. And this is something that I think people that want to follow research, or even if they go to industry, they might need to change from country to country in our field. And this is also something that adds to the difficulty of communicating clearly and well. And so, yeah, I'd like to know the...
So talking about language, well, I have my accent that is the same in French and English. So I think you have to accept the not to be a perfectionist. And you have to accept that it's more important to be able to communicate that not to have an accent, for example. And these I also saw in my colleagues. I mean, it's like when you see presentation by people, then they speak good English, but they have horrible accent and nobody cares. Okay, people complain a little bit, but okay, who cares at the end of the day? So I think accept not to be a perfectionist. Some people are gifted for languages, some are not. It's very difficult to correct that. So practice as much as you can, but I mean, accept. So that's what I can say. I'm sorry, yeah, I mean, it's not easy, but we live with it. And talking about, okay, communication, I'm not very good as well, but I had this colleague that was one in the transparencies, Francois Miranov. It was an older colleague. And he was extremely good in communication. And so all the time when we were repeating talks, he would tell us what to focus on. For example, what is the message? Like, you're talking about this, what is the message that you want to convey? Are you sure you convey it? He was very specific. So even like the title of your slide has to be your message. So, I mean, it's techniques. Then you do up, not everybody feels the same way. Your presentation is your presentation and you do it the way you like it. But keep in mind, really keep in mind that who are the person in front of you and what is the message you want to convey. And he was, repeating with him was very helpful. So, and then again, some people are more gifted than others. I'm not very gifted. I improved a lot over the years. So you just repeat with colleagues, ask them to give you feedback. Don't be frustrated from the feedback. Take the good things. Think about the message. Yeah, and that's about the. And also, yeah, repeating is very important. I can do presentation where I don't repeat much and they are normally horrible. So even a simple presentation, I need to repeat because it's just, I need to have my story in mind a little bit. So yeah, accept to spend time repeating, preparing new slides, because then you will be happy of the results. So, but again, this is not something I learned over the years, and some people are more gifted than others. That's also something like who was asking about countries, something that you learn in the States quite a lot. They're very good in communication, and there are techniques that you can use, make things simple. I mean,
yeah, that's true.
Thank you.
Okay, there's a question here in the chat from Lorenzo. He's asking, is there something you think that was missing during your career in the academic environment? For example, something that could be improved to support young researchers, especially women?
I would have loved to have had a supportive advisor. He was not supportive at all, but it's random. I mean, yeah. I think again, no, I cannot think about a specific thing. It's more like, you know, it's important that young researchers, they show more than old researchers, they do more presentation, they get more practice. And this is not always the case. So that's maybe something that, yeah, I was missing at the beginning, not having someone pushing me and saying, okay, go ahead. Go, try, present. But again, it's sometimes you have good groups where this happens, and sometimes you have standard group where it doesn't happen. The standard is that you have to push yourself. It's not too much the other people. But yeah, money for conference, I was lucky. I always had. It depends on the groups. So in that I was very lucky. I always had money for computers. Okay, I'm a theoretician, so yeah,
that's all you need.
Yeah, but I cannot complain. I always was able to go to the conferences I wanted and buy the computers I liked. So
that's all you needed to be successful. Okay, there's a question by Elena, and then there's another one on the chat. Go ahead, Elena.
Hello.
Hi, hello. So thank you, first of all, very much for your talk. And I wanted to ask two questions that are a little bit related. So the first one is that since you have traveled a lot and you have experienced like different education, how it is in various countries in the world, so USA, but also Europe and etc. I wanted to ask you whether you noticed a difference in general in the environment and in, I don't know, how researchers are seen, how, I don't know, and in general, your life as a researcher, if you have seen like differences in different, or student, for example, in Italy, if you have seen differences. And related to that, if you, I don't know, even if you have ever been in a situation in which you weren't like super happy about the environment you were in, and if so, like what is, because as you were saying, these things are a little bit random, so it can happen. What is your suggestion to like to cope with this kind of situation, and maybe before how to prevent them, like how to, I don't know, look before for a group and see if this could be a great environment to work in. And yeah, so these are my two questions.
So for the second question, I think it's a good idea to interview PhD students. They're normally very good at saying if a group works or not. So I did have moments where it was a bit problematic. And I was asking, my technique has always been, I'm a social person. So my technique has always been try to find someone with whom I can discuss it that can help me. So it can be fellow students, or it can be directly an exchange supervisor. Don't feel that it's that it's necessarily you that don't work if things don't work. So you can try another supervisor, but then depends. But for example, in the States, there's something that is nice. When you are in a university as a student, you are protected. So if the supervisor doesn't work, you can take another one. Instead, in France, you are attached to your supervisor. And once you have the fellowship, you cannot change. So it's more important to choose well. But yeah, my advice is really talk with your colleagues, eventually change supervisor, change colleagues, stop working with people that make you miserable. It's also very good advice. If you feel that someone doesn't respect you or makes you miserable, stop, go work with someone else. It seems trivial, but you don't always do it, because sometimes you think, oh no, I should adapt and so. And regarding the environment, so I didn't, yeah, it's very different, because in the States, I mean, I can compare more. Europe is a bit more similar and the States are a bit more different. So in the States is basically in Europe, once you enter in the university as a permanent professor, you are done pretty much everywhere. Instead, in the States, you have the tenure track. So you still have to prove, after having proved that you're a good PhD student and you can produce a lot of nice paper, you still have to prove that you're a good professor. And it makes people very, very competitive and hard. So I think for me, PhD and postdoc in the States is very nice. If you want to do your career there in a prestigious university, it becomes very competitive. In a medium university, it's easier. In Europe is more okay. Once you're you have a position, you do what you want. So, and it makes people a bit different. They're less aggressive because they're still, everybody's still, scientists are always aggressive. They want to be the best. They want to show off. But if their position is secured, there's a bit less. So that's different for me. I felt that.
Okay, thank you very much for your answers.
Okay, so our time is coming to the end. So I will read out one more question from Gloria, and I'll post the links in the meantime. So the question from Gloria is, did you ever feel like you didn't belong either in the lab in France or the US or at any conference?
I didn't really think I don't belong. No, but this was the advantage of the PhD. Before the PhD, I thought maybe I don't belong. Once I went to the PhD, I said, okay, I did this, I can do whatever. So I stopped thinking I don't belong. PhD is very difficult. For me, it's the turning point, because you don't know yet if you're a student, you are not a student. So what happened is, okay, since this is a women talk, that got me really annoyed was to be in a conference and be the only woman in the conference. That happened to me.
This actually happened to you.
Even lately, and this annoyed me tremendously, because I don't see why.
How many people were in the conference?
Not big, maybe like 60.
1 in 60, wow.
But yeah, exactly. so that was annoying, because yeah, it shouldn't be the case. But some topics in physics are still, the more you go towards theoretical, mathematical, the less women you find. And it's annoying because, yeah, I mean, for me, it's annoying.
Yes,
so,
of course.
It's there's no reason for that.
Yes. Okay, so we're coming to the end of our half hour. So thank you so much, Caterina.
Thank you all. Thank you all for the questions. And yeah, good continuation.
You too, you too. Thank you everyone for the questions you asked. So I posted the link here to our website if you want to know more about our activities. We have social media, we have a mailing list. And also, please give us your opinion on how all of this went here in the forms that I posted in the chat, if you have a few minutes. Again, thank you so much, Caterina, and have
Thank
the
you.
rest of a
Take
nice day.
care. Bye bye. Ciao.
Take care. Bye bye.